Like that number 5 right there?
Yes.
Okay. So what you're going to do in that case is you're going to start off with your molarity, which you're given here, and you're given a volume. So you need to set up your units for molarity. So molarity is your moles solute, liter solution. That's just an abbreviation for solution there. All you know here, so far all we know here is molarity. Right, because we don't have a liter solution, and then we look and we've really got a volume, but it's in the wrong units. Okay? So we want to do a quick conversion on that, and that's going to be 0.1 liter, okay, for your volume. And then what you're solving for here at first is this mole solute. Okay? Because we know everything else. So when you're solving for this, be careful. This doesn't divide out all the way over, it multiplies.
Would it be 1 liter?
0.1. So you've got, if you're starting off with 100 milliliters here, you've got 1,000 in your liter. So there's your 0.1. Yeah, yeah. You got to watch that decimal right there. Be very careful when you're typing. The calculator is just going to give you 0.1. But if you're typing really quick, you really do have 4 sig figs here. So make sure your answer that you carry to this next line is like that, or you'll look at it and you'll go, oh, well, that was only 2 sig figs or 3 sig figs when it's really 4 there. Okay? So you're going to algebraically solve here. So multiplying these two together, that's going to get us our mole solute of the nitric acid. Okay. Should be coming up with 0.6 moles. Okay. And we're asked to go to molecules. Once we're in moles, from here it's really easy to get to molecules, right? We just need what? Avogadro's number. If we were going back to grams, you'd use your molar mass. But since we're going one step further, you actually want to cancel your moles and go to Avogadro's number, because that'll give us the molecules. Okay, your key here was you had to be solving for the moles. That's the only way we can get it into your molecules.
How would we solve for like the molecules of one singular element in the compound?
So if this question, let me rephrase that. So instead, if this question asked for, let's say it asked for now the atoms of which element you want to use?
I do not care.
Okay, let's do nitrogen. Atoms of nitrogen in there. Once you have it down to molecules, it's just one more step. So then you say, for every 1 molecule of nitric acid, how many nitrogens are there?
1.
Just 1. So you have 1 atom of nitrogen. And you'll change that number of atoms depending on just literally the molar count straight out of your empirical formula. I'm sorry, your molecular formula there. Whatever this has in there, that's what you'll throw in there for it. Another way to do this problem is instead of going into molecules is to push back the other way. We can say, what mass is present? It's actually not on this study pack, but what mass is present? So then once you get to moles, instead of going through Avogadro's number, we're going to use molar mass at that point. And you're going to move through that. What else?
What other question?
Mm-hmm.
I have this, so in net ionic equations, when you're breaking down the molecules, sometimes they'll stay together and they won't break apart. So say if it was like I don't know if this actually happens, but if it was like H2SO4 and then by the time you go to the end you weren't breaking it apart, would that only be because it was a solid or a liquid? And that, I think...
Okay. I'm going to do my best to answer your question. If I don't, just tell me.
Okay.
So let me give you an example of an ionic, and I'll show you what you would and would not.
Oh yeah, here. You can have my paper too if you want.
Okay. So you get three things that you don't break apart. You don't break apart solids, you don't break apart liquids, and you don't break apart gases. The only things we break apart for net ionics is the aqueous. It's the only things we break apart. So for this guy, we're only breaking him apart because he's aqueous. You break him into charge. If I was you, I would circle the charge, because when you start putting pluses in between all these and then plus supercharges and stuff, it's really easy for this plus and that plus to get mixed up. Does that make sense? If you're looking at it, so circle it if it's a charge.
I understand that. I'm more talking about like, here I can show you.
Okay.
Just like, how do I know that stays together? Like in the end, it's going to be separated from lithium and that, but how do I not know to separate each four, you know?
Okay, so that is one of your special polyatomics. So when you're doing these net ionics, that's a good question, okay. I see what you're saying now. So for those net ionics, there's two things you want to be looking at. So depending on what type of reaction it is, if it's a single replacement, you want to be looking at your metal activity series. Is this gas strong enough to kick him out? And then for your solubility and whether or not it's going to form a solid or not, whether or not it's going to break apart, you're going to be looking at that second table, your solubility chart. So that piece of that polyatomic you're talking about is acetate. That's the organic way to write it. Either way, it's still acetate. So then when you see that on your list, you follow the solubility rules for your acetates in the solubility rule chart. Does that answer your question?
Yes, it does.
Because your solubility with double displacements depends on the anion. And you look at the anion, and then there are some cations that can make anions insoluble, and some that can make them soluble.
So same thing with like chlorate or
Perchlorate.
Perchlorate, whatever. Okay.
Yes.
You know what I mean? Just like the H and the Cl.
Yes.
Are light reactions going to be on this test?
What?
Light reaction? Specific heat?
No, that's an old exam practice. He may throw some review since we're getting back closer to the test. I don't think he'd throw something like that on there.
Okay.
You might throw what?
Some review. The exam practices that I've seen, I know for a fact he's not going to put naming on there. But since we're getting close to the final again, he may throw some review stuff on there. But it's not likely because this test has a lot on it anyways. So if he's not going to throw naming on there, I know he's not going to throw specific heat on there. There's really not much else that's kind of fundamental that you carry along that you can throw on there that's not already on there. We've already got oxidation numbers. We've already got charges. We already have equations. We already have concentration and things like that. Things that will normally carry through most of the rest of Chem 2. So, yeah.
I have question number 3.
On which exam? Practice.
Yeah, the practice.
I may have a different one pulled up here than you. I went back a little bit. Is my number 3 the same as yours?
Yeah.
Okay.
The last one and then the last reaction. Why is there no reaction?
So you'll have a no reaction in a double displacement if there's no solid form.
That's a single displacement.
Oh, sorry. So, because it's a single replacement, the metal that is trying to push the other metal out of its spot has to be higher on that chart. So if you find calcium and then you find magnesium, calcium's higher, so it's not going to let its little brother push it out of its spot.
Are those all double and single replacements? Second one's neutralization.
No, you got a base but no acid, no acidic hydrogen. Double, single, yes.
So what is like aqueous actually mean? I know that it's like,
Dissolved in water. The only time it doesn't mean dissolved in water is if it has aqueous, then it has another subscript and it says what the solvent is. For Chem 1, whenever we say aqueous, we're talking about water solvated.
thank you.
There was like 2 hands here somewhere. Yes.
Can you explain this question, please?
Mm-hmm. Okay, I'm going to wrap this one up here. So which of these substances would dissociate completely in aqueous solution?
What's the rate of dissociation?
So dissociation is breaking apart into charged ions. The key with a dissociation is water is not a reactant. Now, ionization, water is used as a reactant, so it facilitates the reaction. Dissociation they're breaking apart into aqueouses here, but there's no water as a reactant. Okay? And it follows your same rules. So strong acid, strong base is one-way arrow. Weak acids, weak base is two-way arrow. So because this was a strong acid, has the one-way arrow, okay? This guy's gonna have a two-way arrow, weak acid. So is he going to dissociate completely, or some of that gonna go back? Some of it's gonna go back. So this guy's not gonna be able to do it.
So you're just looking for ones without the two-way arrow?
You're looking for ones that that would, yes, so ones without, yes. So what about ammonia?
It would.
It's not strong, it's gonna have that two-way arrow. Remember, it's your only weak base that doesn't have hydroxide in there. It forms hydroxide as a product, but it does not inherently have it there. And then potassium hydroxide here, another strong base, one-way arrow. So the ones for this would then be A and D.
But I thought you said that for it to dissociate completely, it had to be a base and it couldn't be an acid. 'Cause I know that we asked one whenever doing class
Yeah, because we can't, because we haven't covered pH yet, that's why.
Yeah, that's what he said.
Yeah, but I'm really confused because to me A is also going to
And
dissociate completely because it's a strong acid. And
It-
strong acids, strong bases, and salts dissociate completely.
yes, you're
And
correct.
he said, and he just said that that's ionic, not D. That's why. But we didn't have time to discuss that. So.
And here's why. So what you're using to break all of this stuff apart, whatever you're dissolving it in, is water. Water has inherently partial charges, right? The strongest thing it has is hydrogen bonding. Does that make sense? It doesn't have any ionic bonding. Right? Water, going back to Lewis dot structures, there's no metals in there. This guy can do an amazing job breaking apart this. He can kind of do a moderate job breaking apart this. He will eventually do it, but as soon as you dump this in here, it's all going to break apart. It normally doesn't even need kinetic energy. You normally don't even have to stir it. It's immediately going to happen. With your acids, sometimes you're going to have to give it a little bit of kinetic energy to get the water around all of the acid, because you've got to get this part of this oxygen aligned perfectly with that hydrogen to rip it off. So when we get to acids, if you take the Chem 2 portion, when we get to acids, we're going to talk about that why.
So on the test, if he wants to ask something like that,
If he asks a complete dissociation, you're looking for a strong base because it's ionic. It's one level higher. When it's interacting with two molecules, the stronger force there is ionic. Two hydrogen bondings interacting with each other are strong, but when you have an ionic coming in and interacting, it's going to knock hydrogen bonding out. It's going to go faster because it has a higher strength. So that's why it would be D. Okay, other questions?
Will you kind of go over neutralization?
Mm-hmm.
After that, can you do ionization?
Mm-hmm.
I don't have like a specific question, but
Okay.
I was just trying to like go back over it, and that was the day we had the sub, and I was just, it's not sitting right.
Okay. Is it okay if I do this one?
Yes.
Okay. So in a neutralization, you have to have an acid and you have to have a base. Now, it doesn't matter what order they're written in. What does matter is the arrow. Now, you will have a one-way arrow if at least one of them is strong. So do you have a strong acid or a strong base?
Yes.
yes.
Yes. This guy's a strong acid here. So even though this guy's a weak base, it's going to be a one-way arrow. The strong acid has enough oomph in it that it can push all of that to completion. The only way you can have a two-way arrow in neutralization reactions is a weak acid and a weak base. You have to have both of them weak to get that two arrow in neutralization. So then what you want to do is balance your hydrogens with your hydroxides. So 3 hydroxides, you need a 3 here to get 3 hydrogens. Okay? 3 hydrogens, 3 hydroxides makes you 3 waters. What you have left is 3 perchlorates and an aluminum. And you just want to put those together.
So you put the perchlorate and the aluminum together?
Because the perchlorate is a -1 each, and you've got 3 of them to exactly balance out that +3 on the aluminum. So that'll make your salt.
So as long as you have one strong base or one strong acid, it's a one-way.
One-way arrow.
And it's always making water and
And a salt.
And a salt.
Always water and a salt.
Will you do one with a weak acid and a weak base?
Sure. Just ignore this is here, and I'm going to do one right up here. So we're going to do ammonia and hydrofluoric acid. So ammonia is our weak base. Hydrofluoric acid is our weak acid. Both of them weak, two-way arrow. So this is getting the hydrogen from the ammonia, picks up the hydrogen. This now becomes ammonium. And what you have left here is fluoride negative. And he's telling you you can do this 2 ways. For ammonia, you can do this 2 ways. Either leave it as charges, even in a neutralization reaction, you can leave it as charges, or you can make it the common salt. Either way, it's the exact same thing, because as soon as it touches something, it's going to dissolve. So either way, it's going to dissolve straight back down into its charges. But either way, it's aqueous.
Can you go over which ones can have the two-way arrows? Can all reaction have two-way arrows or just some?
The only reaction that can't have a two-way arrow is combustion. There's no way, energetically, there's no way to get those gases to come back together and form your solids or liquids back together. It'd be nice, but it's the only one you can't. Everything else, like decompositions and combinations especially, right? If I can combine it, I can uncombine it. I can take it back. You can do the opposite of a neutralization. You can have it going backwards because you can have the two weaks coming backwards. Ionizations can, dissociations can if they're weak, but nothing else. But the combustions cannot. The combustion is the only one that can't. Just remember the old adage: you can't put smoke back into a cigarette. There's no way to unburn something. It'd be nice, but there's no way to unburn something.
Thank you.
Mm-hmm.
Can you do oxidation numbers?
Mm-hmm. Let me do, I think she wanted an ionization, and then I'll do oxidation numbers. Let me scroll. So the big difference between dissociation and ionization is ionization actually uses water as the reactant. Okay, I can't stress that enough to you. We'll stress it enough to you, and there'll still be somebody who will get them confused. Just don't. Be the first class that doesn't get them confused. Save yourself the 2-3 points. As soon as you see ionization, you're thinking water is a reactant immediately. Why is this a two-way arrow? That's a weak acid. Water is always weak. Water can act as a weak acid or a weak base, but your primary guy here is this. He's the guy that's really ionizing. If he's not one of your 7 strong acids, two-way arrow. Okay, he would have had to been one of our 7 strongs. So if he is the acid here, he's giving the hydrogen to the water. So it's going to lose a hydrogen. So it's going to become one less hydrogen. The hydrogen's not coming from this 6, it's coming from this in front here. And the water starts off with 2 hydrogens and a neutral charge, so gaining a hydrogen and a positive charge will look like that. It does not matter which way you write the products in. What matters is that the stuff is moved right and you've notated your charge. Okay, so this would be an ionization of a base. We did a ionization of, this would be an ionization of an acid. We did an ionization of a base just a second ago, but I'm going to do another one. I'm going to intentionally do ammonia again. One way or two-way arrow? 2. Weak base. Now this is the case in which water is actually going to act as the acid, right? If ammonia is acting as the base, he's not going to give up the hydrogen, he's going to accept it. So water is going to donate that hydrogen. So this guy picking up a hydrogen and a positive becomes our ammonium. And the water, having lost a hydrogen and a positive, now becomes negative. The reason that ammonia acts as a base, even though it doesn't have a hydroxide, is because it produces that hydroxide. Whenever it touches some water, it will rip that hydrogen off that water eventually. Sometimes it takes a little bit of time, and it will produce that excess hydroxide, which constitutes it a base.
Will you do a decomposition problem?
Yes, there was something, what did you, oxidation numbers and then a decomp.
Okay.
Okay. Yes. So oxidation numbers are really important on 2 kinds of reactions. Oxidation numbers are really important on single and double displacements, because what you're doing is you're changing different things that may have different charges. Okay, so let's get one here. get this one. I'm going to key in on this one right here. So this potassium coming in and kicking that lead out. So if you're looking at your exam study pack, you want to find potassium and find lead. Lead's going to be relatively low. Potassium's going to be relatively high. So this potassium can kick this lead out. Now before you do anything else, what's the charge on that lead right there? +2. We know it's a +2 because the charge on that nitrate is -1 each, and you've got 2 of them. Okay, so even if you don't know your common states for your lead, use your anion to make it give it away for you. Okay, so then that's going to tell you for this potassium, it's +1 though, right? So we only need it in 1-to-1 proportions with your nitrate. So then that tells you immediately you've got some balancing to go on there. Okay, and that'll help you. That'll help you with that. Sometimes it's not going to end up that easy. It's not going to be that easy, that 1-to-1. Sometimes you're going to have something that's a 2, and you'll need the multiples.
I have a couple of other oxidation ones.
Okay.
Cu2SO4.
With doing what?
Just like finding out the oxidation
Okay.
for each of them.
You have a couple more?
I don't know what CE is.
Cerium?
CE and then let's see CrO4 subscript 2.
You may have one more.
And then NH4 subscript 3 and the other
Phosphate.
side gets yeah.
Okay. And I'm assuming this one wants the sulfur, that one wants the chromium, and this one wants the phosphorus. What is it wanting the oxidation states for? Or let's just do all of them. How's that?
Each one of them, yeah, that's what it's one.
So we're going to do copper first for this one. So kind of X out your copper. If you're solving for it, you can't look at him yet. What's the charge on the sulfate polyatomic piece? -2. If this half is -2, and then you have to distribute that evenly between 2 people, what are they both each going to have to be? Well, if they're each +2, that's too much, right? +1. If they're each +1, then they can carry it. So that copper's got to be +1 there. Okay? Now, let's do the sulfur. So if you're solving for the sulfur, the easiest way to do it is with a little bit of algebra. Okay? So if you know this whole sulfate piece is -2, say you're solving for your sulfur, you know the whole thing has to come up to be -2. What will you always know the charge for oxygen? It's always going to be -2. And if you've got 4 of them there, you know it's contributing a -8 charge, okay, in total. So 4 oxygens contributing -8. So 6 would be our sulfur. So 6 minus 8 is going to give us that -2. Just solve that. And your oxygen for this one will always be -2. Okay? Now, cerium, you can either solve or you can look at on the periodic table. Where does cerium pop up at? Oh, I'm sorry, you can't. Never mind. It's a F group. It's right there, element 58. I was thinking cesium. Sorry. So we'll have to solve for cerium because it can have multiple oxidation states. So what is your charge on chromate? Be careful. This isn't dichromate. This is just chromate. It's kind of a weird one. -2. Each piece is -2, so if you got 2 of them at -2, this half is -4. Does everybody see that?
How do we know chromate's charge?
It's on your polyatomics list. If you don't have it for this one, definitely start flashcarding your polyatomics list. There's multiple people don't have them. I don't mind to post them on course content. It's kind of it's a long list, but I'll mark out the ones you don't need until Chem 2. But yeah, these are definitely important. It may not be on this test, but it will definitely be on the final. Okay. So if this half is -4, what does the cerium have to be? +4 to balance that. Now then you can solve for the chromium piece the same way we did the sulfate piece here. Okay, I'm going to go under it. So if you're solving for the chromate, we don't know what it is. But we still do know the oxygen, right? Just do one chromate. Don't try and do both pieces. You can do both pieces, but just do it as one chromate. So chromate minus 8 for the charge from the oxygen has to equal -2. What is chromate?
Why does it have to be -2?
Because just the charge on one chromate. What's the charge on just one chromate?
Obviously.
No, the whole polyatomic.
Oh,
CRO.
-1. Or -2.
-2. The charge on the whole chromate is -2, so that's what you have to come up with, just like we did for sulfate. Does everybody see that? So then, when you solve for it, chromate's going to actually have the same charge here as your sulfur did up top. It just happened to work out that way. Oxygen's still going to be -2. Okay? If you're looking at these, you're going to have a couple for this one. So if you look, ammonium's also on your polyatomics list. What's the overall charge for ammonium? +1. If this whole thing is +1, and let's say you didn't know nitrogen, say it's, for some reason it just slipped your brain. What is the charge on hydrogen always? +1. If you've got 4 of them there, and your overall charge is +1, what does nitrogen have to be? -3. It has to be. Anything else, and we don't get that overall +1 charge. Okay? You're going to solve the phosphate piece exactly like you did the chromate and the sulfate piece. This is the way you'll solve all your polyatomics, okay? So phosphate, you don't know, that's what you're solving for. You do know your oxygen, right? It contributes -8, but this time, what's the overall charge on the phosphate polyatomic? -3. So then, what -8 gives us -3? +5. Is that a little bit better? If you're really struggling with these polyatomics, break them down algebraically like that, and you're going to see it. As soon as you write this, I could see half of you all go 5. Right? As soon as you saw that. But if you're trying to look at it in there, you're like, okay, break it down into, you're just interested in that part. And there's half that thing that you know. You're just solving for one thing, right? Okay.
Decomposition.
Thank you. So there's 2 ways he can ask you to do decomposition. He can either tell you what it will break down into, or if he doesn't tell you, you assume it breaks down into elemental form of each thing. So if you're going to decompose this ethyl alcohol here, we're going to assume we take enough energy to break it down into elemental form all the way across. So we're going to break it down into elemental carbon. Elemental hydrogen, though, is diatomic. Okay? So is elemental oxygen. So you got to treat them like that. Once we know what pieces we're breaking it down into, we need to balance this. Okay? This side's got 2 carbons. We need a 2 here in front of that carbon. This side's got 6 hydrogens. So we need a 3 here. Now this side's only got 1 oxygen. Now, there's 2 ways you can do this. You either see that there's 2 there and you really need half of that, or you can go back through and multiply everything by 2. Whichever way is easier for you to see it, okay? Because if I put a 2 in front of this,